Hello everybody! The long-awaited time is finally here. We are now going to be diving into the world of artificial intelligence. In this project, we are going to be looking at a very simple type of AI, logistic regression. Now, logistic regression is a major aspect of machine learning today, being incredibly advanced in some areas and quite easy to understand in others. So sit tight as we explore the complexities of this machine learning algorithm. Let's get into it. Now, in machine learning regression problems, there are two main categories. One is linear regression, and the other, which we are going to be using in this project, is called logistic regression. Now, linear regression refers to predicting an outcome based on information over a continuous range. In a way, it draws the line of best fit to perfectly represent the data it has been given. So as we look at this image, right, we have a scatter plot full of random data, but it sort of follows a general trend of an upward linear graph. That is exactly what linear regression does. Recall from basic math that a linear function is defined as y is equal to mx plus b. What the linear regression model does is that it selects the m, or slope, and it selects the y-intercept, or b, to best fit the line to the data, which allows the model to best evaluate or predict certain outcomes based on X information. So all that linear regression is doing is choosing the M and the B to allow the model to best fit the data. Cool so far? Awesome. Now take a look at this graph. We can't really make a straight line that accurately fits this, huh? If a straight line goes from top to bottom, we leave out a few key certain elements of the data. But instead of losing all hope and patience, which is what I did when I first learned this, let's take a look at this function, this sort of curved, interesting looking function. This is called a sigmoid function, but what it does is just a general shape of the graph. What I want you to pay attention to is how this function is doing a much better job of fitting to the data, as opposed to a straight line, that is. So logistic regression, in other words, is a classification algorithm. Taking in a few categories or data points, or hint hint, genes, the model can predict categories like healthy or diseased. Now, I hope you can sort of see where I'm going with this. Logistic regression, in short sentences, serves the purpose for classification. Whether it's an email, whether deciding if an email is spam or not, or disease detection in our case. Logistic regression is the way to go. Now, let's take a closer look at this interesting sort of function itself. Okay, so as I mentioned, this main function that is going to be used in linear regression is something called a sigmoid function, which is a pretty weird name. As you can see, linear regression, or a straight line, wouldn't really do a good job of connecting these green dots, but a sigmoid function fits in really nicely. Now, what the sigmoid function is doing is it takes our input values and produces a output value within 0 and 1. If the output value crosses the certain threshold value set, it is taken as a 1. If it doesn't, it is taken as a 0. It really punishes super values such as 0.8, right, which automatically pushes it towards the 1, or 0.3, which automatically pushes it to a 0. Thus, if your output value is a 0.3, you are classified as healthy, for example. If it's a 0.8, you are classified, unfortunately, as diseased. That is the sort of classification method that the sigmoid function does. So, pretty simple, huh? Okay, great. Now that we've looked at logistic regression as a whole, how do we measure the accuracy of our model? In other words, how can we actually evaluate how good our function is? We can actually use something that's called a confusion matrix. Now, a confusion matrix is actually used to evaluate classification models, including linear regression. Now, a confusion matrix is a table, as seen below, that organizes the results of the model into 4 main compartments. Let's take the example of multiple sclerosis disease detection, since that is what we're going to be using or exploring in our project. So first, n. This n value, commonly seen in math, just signifies the number of terms that our model has predicted, right? So as we can see here in this example, 165. All that means is that our model has predicted 165 values, which are being split up evenly among this confusion matrix. So let's get into it. So the first thing is a true negative, which you can see up here at the top left corner. So a true negative indicates that our model was able to correctly label 50 cases as healthy. So just taking a step back, what we have done and what we're using in our data is something called labeling. Remember when I showed you that data table, we had described a certain data point in our data called outcome, and we labeled that data as either 0 or 1 depending on the values of expression. That means that our model is using something called supervised learning, where the model actually can see after it's predicted the correct answer, because we as researchers or data scientists have entered whether or not our values are 0 or 1. So when in the case of true negative, that means that the model was able to correctly identify 50 cases as healthy. So branching off of this, a true positive indicates that the model was able to correctly identify 100 cases as diseased. Now, false positives, on the other hand, means that the model has identified 10 cases as diseased when the patient was actually healthy, which is not good for anyone. Now, false negatives can actually be more dangerous, as it means the model has incorrectly told someone who actually has the disease that they are perfectly healthy. So I hope you can sort of see why it is super important for us to analyze our network for complexities to see how it can be improved and advanced to get the best results possible for our model. Okay, so to briefly summarize what we have learned, there are two types of machine learning in regression prediction: logistic and linear regression. Linear regression is for continuous cases like the price of a house, which is not a definitive choice such as healthy or not. That is called logistic regression, which has binary outcomes. Now, a logistic regression uses something called a sigmoid function to output probability values between 1 and 0 and pushes them forward as either 1 or 0. Now we can use something called a confusion matrix to evaluate our model and see where we need to improve. The main terminology associated with a confusion matrix include n, the number of terms, true positives and negatives, along with false positives and false negatives. Now I completely understand if you do not really understand it yet. I didn't understand it until like the 5th time I had watched it and learned about it. So I highly encourage you to take a step back and go back and read more about false positives and false negatives until you fully understand what a confusion matrix is and how to use it. Okay, great. In our upcoming videos, we are actually going to be coding the entire model from scratch to completion. So stay tuned, we are finally getting into the coding after learning all about MS, the biology behind it, the disease of MS. We have learned about data manipulation, data classification, and now we have learned about AI, and we are finally ready to code. Thanks, and I'll see you soon. Okay, so before we just jump right into the Python, let's take a look at this GitHub link. This GitHub link has access to all of the machine learning stuff that you're going to be needing for this project. So let's take a look. Once we go over to the GitHub, right, we are treated with this abstract of a study that has been conducted using this machine learning model, and it goes into depth about why we really need machine learning in disease detection in the field of biology, and it's very interesting. You should read it when you have a chance. Okay, now what's really important is this msdata.csv file. This is the data file that we're going to be using for this project, so it is critical that you download this CSV file and store it in a place where you can use it. Now this machine learning in Python file basically is the actual encode that you're going to be creating. You can download it and use it as a reference, but please follow along because if you want to get the most out of this course, you would learn how to code this project from start to end. So unless you really want to look at the code, if you have errors or if you're a little bit confused, download this for sort of a reference after the project is done. Okay. So just as recap, download this and download this if you have to. Okay, great. So now that that's done, let's go into our Jupyter Notebook and get started. All right, so let's jump into it and let's open up our Anaconda Navigator app right here. As it's loading, just take a minute to just confirm that you've stored your CSV file in someplace safe. Okay, great. So we can launch that. Awesome. So now we can just head over to the exact folder where you saved your CSV file. So in this case, it's my Python stuff, and you can click new, So go up here, click new Python kernel. These other ones are sort of just terminal, folder, and text files, which aren't really relevant to our coding. So we can just select the Python 3 kernel for now. It might be a little bit different depending on what type Python type, you have, but there should be some sort of Python IPY kernel right here, and that's what you need to click. So for those who are unfamiliar to Jupyter Notebook, this might look a little bit interesting, but we'll break it down step by step. So this as a whole, this sort of interface right here is called a kernel, and each one of these rows are also called kernels. So it's a little bit interesting to see. So let's rename this project. If we just go over to Untitled, we can rename it, let's say MS Data Science Project. Nice. Okay. So the first thing we want to do is import basic libraries. And these are where you are going to be importing all of the important libraries that you can be using throughout this coding project. So the first thing is pandas. Import pandas as PD. So the pandas is really going to be just mainly allowing us to get access to our CSV file and really look at it inside our program. Next is NumPy. Import NumPy as NP. And now NumPy is going to be very important when we start to separate our data. It'll be important when we're doing some of the mathematics behind the data calculations, and it'll just be really important. So next we want to import the plotting libraries in case we do want to plot. So that's import matplotlib.pyplot as PLT. That's pretty much it for now. Oh, wait, almost forgot. Since this is a Jupyter Notebook, we can't just have matplotlib just here. We want to have all our graphs in line, which means that as we go through our project, we're going to have all our files inside this sort of browser itself and not in a different window. So in order to keep all our graphs in line, we're going to have this symbol right here, matplotlib inline. That's it. So in order to run this specific line, you're going to click Shift Enter, and this little asterisk is indicating that it is running right now, and it should be running pretty soon. It might take a while since you're importing a lot of stuff here, right? But once that's done, you can just sort of let it sit. So, and yeah, here we go. So as you can sort of see, once there is a number in that little square bracket, that indicates that this kernel has been run. So that's pretty much it. And as you can see, it automatically generated a new kernel for us once we've actually run this. And we can sort of experiment with this. If we keep on pressing Shift Enter, it'll keep adding more and more kernels, which obviously we don't really need. In order to get rid of a kernel, you can actually scroll up here to that scissor button at the top, and you can just click, 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 all the way till you're back to 1. So that's pretty cool. And also, you make sure to please make sure to save it whenever you want. I think it does autosave, but you know what? It's just better to be safe than sorry, right? Okay, great. So now what's interesting is we want to get our data into our Python project right here. Keep in mind that this course is designed for people who know a little bit of Python. You don't need to know a lot, but just a general syntax should be really helpful when you're doing this course, but we'll walk you through it. So here we're going to be data gathered from GEO data set. And all we're going to be doing is identifying the variable data is equal to pd.readCSV. Now this is a function that allows our program to read a CSV file that is stored inside our computer. And if you downloaded it from that GitHub as I asked, your data set should be called msdata.csv. Okay, great. So now we can actually just run that to see if it works, and perfect, it does. We can see that number in the little square bracket right here, and that indicates that our CSV file has been able to be read. Now what we can do to actually just check if our data set is remotely correct, we can actually do a really cool function called data.head. And what this function does is that it presents to us the first 5 rows of our data set. So if you just click Shift Enter here, yeah, it works. We get the first 5 rows, and we can clearly see, we have all our genes, their various levels of expression, and lastly but not least, we have the outcome, right? with 0 indicating a healthy patient, excuse me. So this is great. This is fantastic. We're getting our data set and we have successfully imported it. All right. So now what we need to do is we need to separate our actual data from the label. Because as I mentioned earlier in the few earlier videos, we're using something called supervised learning. And in supervised learning, our machine learning algorithm learns from the labels that have been provided. But if we have the labels inside our data set initially, it can just cheat and look at the labels right from the get-go. So we need some way of separating our data from the label outcome. And luckily, you guessed it, there's a really cool function to do that. So we can actually, let's set a comment here, isolating data, or separating, yikes, if I can spell, separating labels. Awesome. So what we want to do is, let's say x is equal to data.drop. And this function allows you to drop any one column from your data, or actually it allows you to drop any one row initially. We'll get into that in just a second. But we want to drop our column, in this case, outcome. So outcome. Now, if I just do this, it'll give me an error, I think. Yeah, it'll give me an error because what we have here is there is no outcome called, there's no row, excuse me, called outcome. And you might be wondering, well, why do we need that? Can't the code just see, there's an outcome right here. Why can't it just drop that column? Well, actually, the way Python works is that it looks at rows first. So if we want to identify and we want to tell the program, no, we want to drop the outcome column, we actually need to specify that by saying axis is equal to 1. Because on default, axis is equal to 0, which indicates rows. So our outcome, axis equal to 1, if we run that, no problems at all. Next, we can actually isolate our outcomes in its own little data set by saying y is equal to, actually let's do lowercase, y is equal to data and then outcome. So what this does is that it takes only this outcome column and it just makes it equal to its own little data set. So here you go. We can actually check that out by saying y. And if we click enter, we actually see right here we have 0, 0, 0, 1, 1, 1, 1, 1. So that is our y. And if we do x dot head, we can actually see it has everything except the outcome column, which is exactly what we want. So perfect. We have successfully isolated the outcome from our data, and we have successfully isolated the outcome for our labels. Great job. Now what we want to do is we want to actually import random split. So let's take a step back. In neural networks or machine learning as a whole, we need training data and we need testing data, right? That just makes sense. In our testing data should be pretty much a good split of our data. So what we want to do is we want to call a function from sklearn.model_selection, selection, import train test split. So pretty simple function, but we do that, right? And it's running right now. Let's wait for it to run. Boom, there you go. So from sklearn.model.selection, we are importing a function called train test split. And what this function does is it takes our massive data set, right? And it effectively, which is 5 rows by 32 columns, right? Or actually, if we want to see how big our data set is, we can just click data. And this displays the entire data set that we have here, right? So it's actually 27 rows by 32 columns, right? And we need some way of statistically splitting up that data set into training data and testing data. And that is exactly what our training test split function does, which is named pretty appropriately, isn't it? Okay, so let's just comment that out so people know what our code is doing. Importing random split, let's say. Yikes, my spelling today. Okay, great. So now what we've done is we've imported that train test split function, and all we need to do now is actually split the data. So the way we can do that is split data. So this is pretty tedious in the sense that it requires a lot of syntax here. So I'm just going to type it out and you guys can just sort of follow along. Okay, so capital X underscore train, X underscore test, Y underscore train, Y underscore test. Now these are all different types of data sets, right? We have X train data set, we have our X testing data set, we have our Y training set, and our y testing set. And you can sort of see that these x training set, given the fact that it's only data, is going to be only data. Given the fact that y is data, it's only labels, we can sort of assume that the y training is going to be the labels for that x training. So pretty similar with the x and y test. Okay, great. So here's where the syntax comes into play. We're going to do, actually we can just copy paste this. We can just do train test split. And in our function, if you want to see what this function actually takes, Jupyter Notebooks has a very cool sort of functionality where if you click shift and tab, you can actually see what exactly the program wants. So as you can sort of see here, if we scroll down, this is exactly what it wants, right? It wants, as you can see here, it wants the x data, it wants the y data, it wants the test size split, and it wants the random state. So we can actually just copy paste all of this right here and put that here. Great. And let's go into it piece by piece. So x is our x data, right? They want to see what is your data. They want to see what is your labels, right? So these two things are your data and your labels. Luckily, in line 7 right here, we have actually identified our x is our data, as all our data except the outcome labels. And y, conversely, is all our data, excluding all our data except the label outcome. Now, the test size function, or the test size parameter here, is explaining how much of your data is going to be devoted to test. So for example, right here, it's set to 0.33. We can actually just set it to 0.3. I think that's a pretty good amount, right? 70% is for testing and 30% is for, 70% is for training and 30% is for testing. Now, random state is it's a pretty important function, but we can just leave it for 42 for now. But yeah. So now when we run this, right, we have now access, that went pretty fast. So that now we have access to 4 different data sets and sets of data, which we can use for our model. So now you're probably wondering, where is the actual logistic regression model? Good question. That actually comes from sklearn itself. So here we can say import model. So now what we're going to do is from sklearn.model import logistic regression. Awesome. So what this does is very similar to the train test split, right? Our program is now calling the logistic regression model from the sklearn library. So that's pretty much all we're doing in this. And we can actually set it equal to, so let's say if we want to reference this logistic regression, code, right? We can just say log model is equal to logistic regression with brackets. And that's all we need to do. Oh, we seem to have an error here. I think there is, yep, right here. So it's actually sklearn.linear_model. This should work. Okay, much better. So yeah, sorry about that little error there, but this is pretty much it. Just syntax. So sklearn.linear_model, import logistic regression, log model is equal to logistic regression. So we're basically instantiating that logistic regression function inside of log model. Awesome. So now that we have our actual model, right, and recall that sigmoid function, that little squiggly line function, that's pretty much all log model is. But now we need to fit our data into this function. So what we do is fit data. All we need to do now is say log model dot fit. And what we want to do is we want to fit the X training along with its Y labels, which is Y train as we've identified here. So that's pretty much all it's doing. And if you click run, you can actually see this output that it's giving, right? It's saying logistic regression, and this certifies that your logistic regression model has been fitted with this data. So at this stage, your model is actually ready to be tested. So how do we test our data? We can actually get some predictions. So let's say, and I want to emphasize at this stage in your program, right, we actually have a working model. So what we've done, let's just take a general recap. We've imported our basic libraries. We've taken our data from the dataset from that GitHub, a dataset which you yourself know how to create thanks to the last few videos. We have our dataset right here. We have isolated the data from the labels. We have imported the train test split function. And in reality, of course, you can split your data yourself, but due to time, this function is pretty simple, and it's quite convenient. So here we're actually splitting the data. Here we're importing the model, the logistic regression model. We're calling it, and here we're actually fitting the train split data that we took here, and we're fitting it into our model. And we can see by this output that we actually have a working model. But now let's actually get some predictions, right? We want to see this model in action. So here we can actually say predictions is equal to log model dot predict x underscore test. Now what is this doing? Recall that in here, right, we split our data into x training and x test. And all of these x train and x test are literally just rows and rows of data, right? So if we fit in our x test, we can sort of see it works. And let's see. So predictions. So given all those values, right, all of these values that has been entered into our model, it is now predicting a healthy patient, a healthy patient, a healthy patient, a diseased patient, a healthy patient, diseased, and healthy. So we can sort of see here that there has been 1, 2, 3, 4, 5, 6, 7, 8, 9 different rows that have been entered, right? So 9 different instances of our data, and the model has accurately predicted, or we don't know yet, but it has predicted 9 different outcomes. So now that we've actually found our predictions, let's evaluate it, right? We want to get classification reports. We want to see how exactly did our model work, and how well did it do. Are any of these correct? Let's check it out. So here we can say classification reports evaluation. Okay, so the cool thing is sklearn comes with a lot of stuff, right? They come with they come with the train test split model. They come with the logistic regression model. Here we want to incorporate their classification report and as well as their confusion matrix. So from sklearn.metrics import classification report, and we're going to be taking a look at that. That is just basically like a report card for your model. That's pretty much it. In addition, we also want to get that confusion matrix. Keep in mind, in our last few videos, we had gone over what a confusion matrix is, those true positives, the true negatives, the false positives, and the false negatives. And we want to use those terms to evaluate our model. So what we want to do, let's say print model general stats, right? Here we can print out our classification report, pass in y underscore test along with our predictions. So what exactly is this line doing, right? In order to actually get a classification report, we need to compare two sets of data, right? We need to compare, what your model is supposed to get and what did it actually get. And if we recall our train test data set right here, we can see y test here are basically the labels and the correct answers, in a sense, the correct answers for your x data, which we just did right here. So we entered x test, into our model, and it has spit out these following predictions. The true predictions, and the true answers, I should say, are actually y test. So we are comparing y test, the actual answers, with our predictions. And that's going to give us, and then we're going to see the results in our classification report. Now we also want to see something we're quite familiar with, our confusion matrix. So print, pretty similar code, confusion underscore matrix. And now we want to pass in the same parameters, y test, along with predictions, because we're just comparing the true correct answers with the answers that we got. And now, moment of truth, run. And boom, there you go. Actually, this is super cool. We have 100% precision, 100% recall. And if we take a look at our confusion matrix, right, we basically have no false positives and false negatives. So basically this means that all our code is 100% accurate. Now, a general note. Let's take a step back and actually evaluate this. This means that our data set in our model is actually 100% accurate. But in the real world, you rarely ever get such scenarios. A little bit more on that a little bit later. But for now, let's take a general recap over everything that we've done so far. In the beginning, we have imported our basic libraries. We got our data from the MS dataset CSV file. We were able to drop the labels and isolate the X and Y datasets. We imported the train test split model. We split the data. We got our logistic regression model. And finally, we added the predictions. And we got our general results, which seem to be blowing it out of the water. Now, most people would seem, okay, we have 100% precision and 100% accuracy, right? What is the problem? Well, in machine learning, you rarely get such perfect scores. And, let's dive into that right now. Awesome job, everyone. You should feel really proud of yourself for sticking with the course so far and finally creating that logistic regression model that is able to classify multiple sclerosis based on gene data. It's been a super long journey, but one little caveat that we haven't really discussed yet is actual usability. Obviously, our model is far from actually being used in a medical society, right? And the reason for that is because we simply do not have enough data. If we had, we only had like 27 rows and 32 columns, right? In an actual MS real project, right? This is an example of a CSV dataset, and you can just see the vast expense. There's just a huge amount of data, and this project is nowhere close. It only has 892 rows, right? And it's nowhere close to the amount of data that would actually be needed for a real life medicinal project. So I want to emphasize, half of machine learning as a whole is just data collection. 95% of it is getting accurate data, because if you have accurate data, the rest really just falls into place. But yeah, that's pretty much it in terms of our project. So let's go over to the slides and we can have a final summary. Good job, guys. So let's just go over a brief summary of what we've learned in this video. So in our model, we've learned about importing data using pandas. We've learned about dropping labels to isolate just our data and our outcomes. We've learned about using sklearn to split the data into training and testing. We've used sklearn to fit data into our model, and we've used evaluation methods like the classification matrix to actually evaluate our model and really see how it works and how well it works. We've also learned that we need much more data to actually produce something that is usable and even worthy of recognition. But the true power of our model is that we've learned the methodology behind it. And if we have sufficient data, this method that we've discussed through the last few videos can be used and should be used in machine learning and disease detection in the world today. So we have finally reached the end of our NeuroMatter series. This has been a major transformative experience, and I hope that you guys have been able to learn so much through this. Some of the things that we have learned include genetics, biology, autoimmune disorders. We've explored the cell and the deep intricacies of autoimmune disorders like T cells, B cells, translation, transcription, RNA, mRNA. We've gone a lot of biology under our belt. We've also looked at a lot of statistics with the GO2 database screening, data selection, how to choose what data sets are good. We've gone through data manipulation, how to hone down our data. We've talked about probability, null hypothesis. We've talked about, identifying if our data is statistically significant. We've talked about log FC values, P values, and much more. And finally, obviously, we've talked a lot about machine learning itself, how it's used in the world today. We've talked a lot about logistic linear regression, the differences, the similarities between them. We've talked about network evaluation using classification methods. We've talked a lot about Python and used logistic regression to classify multiple sclerosis in patients today. And I'm sure you learned much more. So from NeuroMatter and behalf of everyone at NeuroMatter, we thank you for choosing this course, and we hope you learned a lot during your experience here. Go forth, use what you've learned, and shape the world.